Okay, everyone, welcome to Fornicated. This is a project designed to tackle the rampant misinformation and conspiracy theories that flood social media. We do this through application of critical thinking skills, real-world experience, and of course, common sense. So just a quick brief introduction about me. I served in the U.S. Navy as part of Signals Intelligence, specializing in radio and satellite communications. I received advanced technical training in the operation and troubleshooting of complex radio and satellite communication networks in support of fleet operations. This includes air, surface, and shore platforms. Was deployed for multiple deployments, including to the Middle East, to support combat operations there in that same role. And it's hopefully through this lens that I can shine a little bit of light on tonight's topic. While I'm no expert by any means, because an expert implies there's nothing else to learn, I do possess a little bit of expertise, and I hope to apply that. So now, some of you, or probably rather most of you, are somewhat familiar with tonight's topic. After all, it's been coming up in every debate, social media post, and presentation, or to use the Fleur Streets slang of the week, Prezi, everywhere you look. It is the supposed globe killer, the silver bullet to finally expose the globe lie once and for all, the flat earth proof without refutation. Allow me to introduce you to the Battle of the Beams. A debate about geodesic surveying, they bring up Battle of the Beams. A debate about observations of celestial bodies with MC Tune, they add in Battle of the Beams. A presentation about null hypothesis, they insert Battle of the Beams. A dinner conversation in Punta Arenas before participating in the trip of a lifetime to Antarctica, they want to talk about Battle of the Beams. Yes, I'm jumping. But don't believe the hype. As with most flat earth proofs, this is nothing more than a new variation of Robothams we see too far. We know how those end. The bar is open. Grab yourself a drink and some popcorn. And let's get started in an attempt to unfuck the stupidity that is Battle of the Beams. Oh, and don't forget to tip your waitress, Sealion.
I'm wearing a nice cocktail dress, just so you know. I don't have my camera on, but
we'll take your word for it. So the causes of World War II are well documented. We mostly learned these in school. There's a complex convergence of unresolved tensions from World War I, economic hardships, ideological extremism, and basically the failure of international diplomacy. Whoops, I went too far. Too many clicks, my apologies. This period was defined by aggressive expansionism and appeasement, ultimately culminating in the collapse of the fragile peace agreements and the outbreak of devastating global conflict. These locations and events should be familiar to everybody. We're talking about Poland, we're talking about France and Dunkirk. This quote from Winston Churchill's famous speech to the House of Commons in 1940 sums up the Battle of the Beams pretty nicely, and is actually from Tom Whipple's book about the Battle of the Beams. The war will not be fought as expected on land, at sea, and in the air. It would also be fought on the airwaves. It will be fought between scientists on both sides at the forefront of knowledge, which I think is a very fitting quote. So what is the Battle of the Beams? Well, pardon me for a moment, but I really hate the name that they give this, because it's basically taking away from the book, and their sole proof is based on something called Knickerbein, which is just a part of it. So the Battle of the Beams as a whole is a name used to describe a scientific and intelligence arms race between Germany and Britain. And it's during this time that, due to necessity, we saw innovation occurring at an incredible pace. But for all of the Battle of Beams is, which includes things like radar, includes things like the radio navigation, things like that, it's only part of the story. And we're going to be focusing on Knickerbein tonight, since that is the proof that Flat Earth uses. So as with all stories, there is a cast of characters that are going to contribute to the story. Some are prominent, some are mainly a supporting role. In the British corner, we have Churchill and Linderman, among others. However, the two main characters who played a part in this from the British side is R.V. Jones, who you see on the lower left-hand side. He was a 28-year-old physicist with the title of Assistant Director of Intelligence for Science. His position was a very ambiguous task of using his scientific knowledge and expertise to identify and counter German technological advancements. On the upper right, in the sporting hat next to Churchill, is Frederick Linderman. He was a gatekeeper to Churchill. He was actually Churchill's lead scientific advisor, and nothing got to Churchill from the science side unless it went through him. He was coincidentally also the mentor to R.V. Jones. So when R.V. Jones left Oxford, he actually went to work for Linderman before being appointed to his position as Assistant Director of Intelligence. In the German corner, as with most things in history, individuals are not necessarily called out, but we have various characters from both the scientific and military fields, and as well as some signals intelligence individuals. The main character here is Johannes Plendl. He was a major assigned to the Luftwaffe Signal Corps. He was tasked with advancing and overseeing. Sorry, I lost my place. Oh, sorry. He was tasked with advancing and overseeing the development and deployment of new radio navigation systems. Also included in here is Ernest Bruning, who is the head of the radio development for RLM, which was the civilian side of the Luftwaffe. Wolfgang Martini, which is head of Luftwaffe Signal Corps, who Plendl reported to. And we have some other people here that are also part of it, including Hans Ferdinand Meyer, who was a mathematician who worked for Siemens Research Laboratory, and he was the one who actually authored the Oslo report. If you notice that Myers and Plendl both have asterisks next to their name, they both were immigrated to the United States after World War II as part of Operation Paperclip. The last character in the story is the Knickebine system itself. Knickebine was a code name given by the Germans to a particular radio navigation beacon. It translates into English as bent leg or crooked leg, which is derived from the design of the antenna when you view from the top. We'll get into the antenna specifications a little bit later, and I'll show you exactly what it means. To understand Knickebine, it is best to kind of understand its predecessor, the Lorenz Blind Landing Radio Beacon, or LLF. So what the LLF was basically two specific signals would be transmitted across three different antennas. The two outside the antennas are actually acting like reflectors, so one signal consisting of dots and one other signal consisting of dashes. The overlap of the two signals created a constant tone centered on the runway, and the inbound aircraft would just fly along that tone to lead them to the airport. And along the way, they had other receivers, if you notice here where it says VEZ and HEZ. VEZ was set up at 300 kilometers away, and 3 kilometers away, and HEZ was set around 300 meters away from the end of the airport. This way they knew where they were at on the beam as a way of direction finding and as a way as range finding. On the bottom left, you'll see one of their smaller antennas, relatively small. This is their hut that is their transmitters from. It's basically 15 feet by 10 feet. And the antenna itself wasn't much more than 10 meters square. Sorry, I forgot one last thing I wanted to bring up on that last one. So important detail from here that I want to bring up is the timeline of the LFF deployments. By 1937, the LFF system was operational at 7 international airports, including London at Croydon. However, Germany ceased exporting the LFF system in 1938, instead choosing to concentrate on refining it for military purposes. And this is basically where the birth of Knickebine as well as X-Garot and Y-Garot start. During this refinement, German scientists discovered various nuances associated with VHF and UHF frequencies, such as refraction that extended the usable range about 30% further than expected from true line of sight. The Luftwaffe then went about trying to exploit the discovery for military advantage. It's very similar to the LFF. It's actually a very ingenious and innovative adaptation. Instead of an inbound circuit or as an inbound signal, they used it as an outbound signal. So it had the same two distinct lobes of dashes and dashes that overlapped for an echo signal, which is constant tone. And the radio operators within the bombers would fly along that tone until they crossed another tone, which creates a virtual X marks a spot in the air. When they heard the second tone, they know they're over the target area and they would drop their bombs. The LFF system could not accomplish this in its current form because it needed larger antennas and larger transmitters, much larger. So to deploy this, the Luftwaffe Signal Corps provided a very long, very specific list of system requirements for Knickebine. These are outlined in various Luftwaffe memos held on microfiche at the Federal Military Archives located in Freiburg, Germany. One of the requirements to note, and I actually have some of these other requirements later on in the presentation to just kind of glance over to see the extent that are required to do the engineering for this. But one of the requirements of note is for the equisignal horizon beam width of 0.2 degrees. The first few stations, which are often referred to as the large Knickebine stations, were pretty much unable to meet this requirement due to the design of the antenna. Instead, it banked on having a maximum width of 0.3 degrees. The smaller Knickebines were able to get it down to actually 0.1 degrees, but they were actually a much different style of antenna, and call it version 2.0 that got released. Another requirement of note was the system had to be compatible with the Lorenz receivers that were already standard equipment in Luftwaffe aircraft. This was basically ensured that the prompt deployment without having to develop and manufacture new equipment, things like vacuum tubes, receivers, things like that wouldn't have to be they wouldn't have to be allocated for this. They can just use whatever was there. There's one last detail about the system that I found particularly interesting. It wasn't a requirement per se, but the date of the Luftwaffe memo that we see in the lower left here, that outlined the requirements. The memo was dated 10 September 1939. And in the translation, it requested sites to be operational in October and November of 1939. This sort of deployment timeline is completely unrealistic unless you consider the implication that the system had been an active project that's been in research for some time prior to this memo. In fact, Stolzberg was actually midway through its construction when this memo came out. So Ether cosplayers had a 90-minute live stream video discussing the so-called globe killer. During this, our very own Bull Knight made a gallant effort in an attempt to provide technical assistance and even some actual training, all in an effort to help prevent their public humiliation. And it should come as no surprise to anyone that no one took the time to learn from it and they completely dismissed it. Yes, I use Comic Sans for this specifically for this. Since we started with a quote, let's go ahead and start the flat earth side with a quote. According to Alan, it just works when referring to a flat earth. Now, during their video, the Ether cosplayers make multiple claims. One I found especially interesting was the one that Alan made was it just works. And not to worry, we'll address more of this. But there's actual claims that they made that I want to address specifically in this presentation. And it's not just a technical refutation but a complete refute of their understanding of this entire subject. We'll come back to this slide multiple times within the presentation just to see where we're at as we discuss these. But what I'm going to concentrate on is solely going to be the actual evidence presented to Churchill and the War Cabinet, the basis of the skepticism from the War Cabinet, the downplaying of scientific information presented by Jones while placing too much emphasis on RAF measurements. That's a big one. The claim that that radio signals are clipped by curvature, and lastly, just how accurate Nicobine was in regards to Derby. Now, the next two slides are basically images created by the Ether cosplayers as part of their proof. This first one is their understanding of how it would work on a globe. I moved these all into a text form later on in the signal part of it. And then they also were kind enough to show us how it would work on a flat earth. First things first. And if you're listening to MC Toon's debate last night, and you know anything about the EM field and radar and radio, you would almost want to punch your screen as much as I did. A very simple and repetitive, silly claim made by the Ether cosplayers is calling this a radar. I understand I'm being pedantic, but it is not radar. It is a radio navigation beacon. Radar implies a receive signal. Nicobine was transmit only. The only thing that received it was the planes. There was no two-way communication whatsoever between equipment. This is just the first and easiest example of their fundamentally flawed understanding of this topic. One that would be easy to correct and maybe even admit a mistake. But anyone who deals with flat earth knows that didn't happen. So in this chapter, the first chapter we're going to discuss is going to be the evidence. This is going to be the evidence presented by R.V. Jones to convince Churchill, the skepticism of the War Cabinet, as well as the scientific research. Actually, before we get started on this, if there's any questions or any concerns, just interrupt me. Here are the specific claims we'll be addressing in this chapter. Like I said, what I'll do is I'll highlight the ones that will be addressed in individual chapters, and as we go through, we'll see how we tackle them. So let's start with the intelligence that R.V. Jones had access to. First, we have the Oslo report, which was a mountain of intelligence authored by Hans Meyer. Due to the amount and type of the information that was provided, the British intelligence initially thought it was German disinformation released to cause panic within Britain. And while it wasn't entirely correct, the Oslo report provided just enough information to pique the interest of the UK intelligence services, especially Jones. POW interrogations were a pivotal part of the evidence. While most of the prisoners did not provide too much information in their interviews, the listening devices installed in their cells provided a treasure trove of information. Part of this treasure trove was a reference to the equipment used in the HE-111. After being asked about Nicobine, the POWs bragged in their cells that the British will never find the receiver, implying it was hiding in plain sight. When they finally found the Lorenz receiver in the HE-111, some techs basically analyzed it, and they showed that it was about 7 times more sensitive than was required for the Lorenz system. Lastly, we have the Enigma intercepts. They all provided, so some of these intercepts provided specifics, including coordinates of transmitters, targets. They've been, having been part of the intelligence community during my military service, I can tell you that this is hardly circumstantial. This equates to a smoking gun in the intelligence world. Having 4 different types of sources of information all pointing in the same direction, you don't get better. Research in Britain during this time prior to World War II was mostly limited to HF band and lower frequencies, whether it was Appleton's Nobel Prize winning research on the ionosphere or theoretical research into refraction of radio waves at distances. While Eggersley did conduct research pertaining to refraction and diffraction of ultra shortwave radio wavelengths, what we call VHF now, it was mostly about proving theoretical equations rather than actual applications. This becomes important later. British experience with VHF at the time was limited. The Lorenz system was only operational at Croydon for a year before Germany stopped supporting the system. Radar was independently invented by both Germany and the UK, but both were very different in how they operated. UK version, referred to as chain home, and that Alan can speak to at length, transmitted between 6 and 25 megahertz and used 100-meter tall and antenna masts strung along the coast. Germany's radar was actually smaller, and it operated at 560 megahertz to 3 gigahertz. Now, the British military, more specifically the Tizard Committee, who oversaw the early detection innovations like radar, considered radar to be too immature and a low priority. They preferred to explore things like infrared, which was actually Linderman's and Jones's first foray into these things, acoustic mirrors and spotlighting as methods for early detection of inbound aircraft. It wasn't until Linderman, the chief science advisor, was replaced by Appleton on the Tizard Committee that the radar became a priority and was given the resources it needed. Now, one example of theoretical research being done at this time was by Eggersley. This research included calculations for a signal coverage of a 1.5 gigahertz or 20 centimeter signal transmitted from Germany, which would include the theoretical reception of the signal over the UK at 25,000 feet in altitude. This is actually some of the evidence that Jones would provide to Linderman and Churchill to convince him of the beam's use at the time. So when we talk about cabinet skepticism, radio navigation was in its infancy at this time. The innovation of using a Lorenz-type beacon as an outgoing signal was ingenious, to put it bluntly. The command leadership earned their scars during World War I and believed, at least somewhat, that warfare had remained unchanged in the last 25 years. While overestimating their own abilities and underestimating Germans' capabilities, you could almost call it hubris at the time. So, surprisingly, the RAF Bomber Command was the most skeptical. They practically took offense to the idea that a skilled air crew would require something such as a navigation device. These were the descendants of Horatio Nelson and James Cook. Their crews could locate targets using celestial navigation. It wasn't until the Butt Report published in 1941 that a critical analysis was done of the effectiveness of British bombing. It showed that only about 30% of bombers It showed that only about 30% of bombers dispatched hit within 5 miles of their targets. The number dropped to 10 to 15% in adverse conditions. Not exactly pinpoint accuracy. This wouldn't be an isolated event in the War Cabinet erring in their assumptions. From the intelligence alone, Jones was convinced of the beam's existence. However, he had to convince his mentor Linderman before getting access to Churchill. So a lot of things start happening really quickly. Linderman listened intently to R.V. Jones about the intelligence, but he remained unconvinced. He believed that to have the necessary precision of a navigation beacon, higher frequencies would be required, and these higher frequencies would not refract enough to cover Britain. That is, until Jones presented that theoretical research from Eckersley about the 1.5 gigahertz signal from Germany being received at high altitudes over Britain. Once convinced, this led to a note from Linderman to Churchill, who then directed further investigation. The RAF Signals Directorate was designated to take immediate action. What the boss wants, the boss gets. They allocated 2 Avro Anson aircraft and additional resources to put at Jones's disposal. The first flights were scheduled for 19 June, but due to a receiver power supply fault during the first flight, it had to be scrubbed. The next flight on 20 June resulted in no beams being found. So now we find ourselves on the morning of 21st June, and the War Cabinet is convened to discuss the Nicobine threat. The staff was attended by Churchill, command-level military leaders, and scientific advisors. It's here that Jones formally presented his case. Just as he had to Linderman previously. The entire War Cabinet remained skeptical. However, only one opinion mattered, and that was Churchill. He was now convinced, so he issued an order to make locating the beams the highest of priorities, and if located, develop countermeasures. That afternoon, in a separate meeting, because, the military can never just follow orders directly, the Signals Directorate invited Eckersley into a meeting, who was not part of the War Cabinet meeting, where Jones and Linderman also attended. There, Eckersley contradicted his theoretical research and didn't agree with Jones's finding. At least he wasn't confident enough in the theoretical research to stake his reputation, even though he was a radio propagation expert, as a basis for a war strategy decision. From my understanding of what I've read of him and what I've learned of him, it was basically, since Churchill's already convinced, he could cover his own ass and say, nah, I don't agree. But he didn't say it to Churchill. After all those present during this meeting basically said it was a wild goose chase to continue looking for these beams and recommended scrubbing all future flights. Jones, on the other hand, stood his ground, reminding everyone of the order that Churchill had given that morning, giving the location of the beams the highest priority. And Jones felt he knew the most obvious target. In his mind, the factory that built the Merlin engines for the Spitfire and the Hurricane airframes were crucial to the defense of Britain. And that was the Rolls-Royce factory in Derby, UK. So here we go with some of the measurements and calculations. Now, one of the biggest things about the Ether cosplayers' ideas of, they base all of their arguments based on RAF measurements. Now, I understand they're not necessarily maybe used to measurements, and so the idea of using a measurement is a novel idea to them, but let's delve a little bit into these measurements a little more. Now, since Britain was not utilizing the VHF frequency bands, the RAF did not have access to radio receivers or transmitters for the Lorenz frequencies. To accomplish their goal of locating the beams, Jones had to resort to actually purchasing civilian Hallicrafter S-27 receivers from a Webb's radio shop in Soho. In fact, one of his civilian underlings had to basically use a borrowed uniform and go purchase them on the basis that the RAF would pay them back for them later. These were installed in the two aircraft that were allocated to them, of the Avrov Ansons, and the first flight was 19 June. On the night of 21 June, the third night, an aircrew consisting of Flight Lieutenant Buffton and Corporal Mackey took off from RAF Witten with specific instructions to locate transmissions with Lorenz characteristics. As with most things in intelligence work, luck plays just as much of a role as tenacity, and as luck would have it, the beams were located. According to the flight report, they were measured at 400 to 500 yards wide, with one beam located near Spalding and another beam located near Beeston. Now, these are the measurements that are used by the Ether cosplayers for a basis for all their assumptions pertaining to Knickerbein and how it wouldn't work on a globe or the accuracy of Knickerbein. But again, let's get in these measurements and we'll look at the equipment used to make it. Let's start real quick with the aircraft. The Luftwaffe HE-111H is a primary medium bomber used by KG-100 for the Knickerbein missions. Specific to note of this is a ceiling of 8,000 to 10,500 meters, depending on the weight and range. The HE-111 design consisted of two armored bulkheads with the radio operator station located between them. And the air crews also had significant training regimen for navigating on the beams. This was actually noted in some of the diaries that they found of the air crewmen when they became POWs. The Anson used by the RAF to locate the beams was a very different airframe. It was used primarily for maritime patrol with a ceiling of just under 6,000 meters. The design consisted of no armor bulkheads, with the radio operator station located behind the cockpit in an open air environment surrounded by windows and ambient noise. Remember, this aircrew also did not have specific training. In fact, they weren't even briefed about Knickerbein. They were told, go find Lorenz type signals. Now, the difference between the receivers are just as varied as those of the aircraft. I'm going to try to keep this at a very high level and keep the nerd porn down to a minimum, but there are some important parts of this that need to be pointed out. I'm sure no one really cares about the difference between the different types of vacuum tubes used in these, but I'll try to keep high level. Starting with the FUBL-1 receiver, it was purposely built for Lorenz military applications. It used advanced circuitry design. It had multi-stage amplification. It had integrated antennas, and it had extensive shielding for EM interference. The S-27 receiver was a civilian receiver. It was built for use in controlled environments. Its features included a broader frequency range, moderate signal processing capabilities, a lack of extensive EM shielding, and had to be spliced into existing systems. In fact, the receivers had to be modified from AC to use the 28-volt DC system of the Anson. This was the same modification that led to the failed mission on the first mission for the 19th of June. So are these measurements or observations? In order to obtain accurate measurements, specific challenges need to be overcome. Things like ambient noise, radio operator experience, receiver sensitivity, EM interference, antenna type, and even the age of the radio operator himself. Since pictures speak 1,000 words, I believe the pictures of the radio operator environments on the right would speak volumes as far as the challenges faced by the RAF. On the top, we have the Anson here. You see open air, you see nothing but windows. And this right here is where the radio operator sat. This is inside the HE-111, armored bulkhead fore and aft, and the only open air space is for the turret above him. Needless to say, his area was much more quiet than in Anson's. Now, considering all these facts, differences in airframes, differences in equipment, differences in training, what they were actually there to look for. Should these be considered measurements or observation? Would any reasonable person accept a beam width measurement of 400 to 500 yards as an accurate measurement, much less the basis of a denial of curvature of a spherical Earth? Or should we call these what they really were was basically an observation.
Let me just pause there, I think, because I think that's the crux of the presentation, and excellent job, especially with the historical background and discussion there. I just want to point out that the incredible double standard of the Aether cosplayers, that they completely put forward this as a, definite, it's a globe killer, this 400 to 500 measurement is what they call it. But when we show them a measurement from a theodolite or GPS or any other system, what do we hear? It's just endless nitpicking on all the details. So I just wanted to point that aspect of the double standard out and see what your thoughts are there, because like when you look at all these, I mean, there's so many sources of uncertainty that go into this that Walter Lewin in his I think it was his first MIT OCW lecture says a measurement without uncertainty is meaningless. And they want to talk about the null hypothesis, but they can't even tell you what any source of error in this measurement would be, or any level of uncertainty analysis whatsoever. So I just want to emphasize that point, but I don't know if you have any thoughts in that regard as well.
Well, and actually, let me bring up another point. When they first, went up in the air and they located, so when they went and located this, the first beam over Spalding, they were basically, it was a cloudy night. So, the idea of a 400 to 500 yards beam is, you have some guy in the back here, sitting with headphones on, dialing into a radio, trying to find the right frequency to see if they can hear a tone. And then when they hear the tone, they hear the dots or dashes, depending what direction they're coming from. And then they finally hear the echo signal in the middle, the constant tone. Now they're guessing time versus distance, right? So they're looking at how fast they're going versus, over the time that they're going to figure out the distance of it and the width of it. But again, like you said, it's not necessarily a measurement. There's a lot of uncertainty there. We're talking about there's no point of reference because the skies are cloudy. We're talking about some guy looking at his watch while looking at the entire, dials and gauges in front of him. We're talking about a radio operator who's concentrating, probably with his eyes closed, trying to make out the signal within the static and within everything else and discern a signal that he's never heard before to identify what is the echo signal and what isn't. There's so many variables that goes into this. It's amazing that anybody would base this on any sort of a proof of anything.
Yeah. Got to remember that all the Anson's going to know is it's indicated airspeed. He might be able to get a bit of a guess at his true airspeed, but he's not going to have a lot of a clue what his ground speed will be.
Right.
Not at night in cloud.
Right.
In 1940.
Right. And again, and like I said, I think these pictures speak speak multitudes of the environments that we're dealing with. The picture at the top is the environment that the RAF had, surrounded by windows in a reconnaissance plane, surrounded by ambient noise with headphones on, versus the HE-111, which had armored bulkheads and a relatively quiet environment to be able to listen to these things. They couldn't be further from each other. Okay, so now let's get to the technical portion of the presentation. Again, I'm going to try to keep from delving too far into the nerd porn and instead try to simplify this portion. I know not many people are licensed FCC techs or operators or have much RF experience. However, I will do my best to keep it relatively high level. Now, I'm not one for reading slides specifically, but in this case, I'm going to. So I want to go over kind of what the FE claims are. And then after this slide, we'll go ahead and start discussing some of the signal properties and then come back to the slide later to see how the questions on the right side of the slide are answered. Now, the FE assumes that VHF frequencies are bound by optical line of sight properties. In fact, they use an optical curvature calculator to assume its distance. I want to note that they use a 200 meter elevation to give, quote, the globe the benefit of the doubt. At 200 meters, the tangent to the horizon is at 32 miles, 51 kilometers. I prefer metric. They also state that curvature would clip the radio waves at the optical horizon. This means that the center of the beam, where it clips where it would be the tangent to the horizon, all signals below that center of the beam would become, given a haircut, missing, be reflected backwards, shoot off into space, I don't know. But they suggest that it would be clipped. Flat Earth also assumes that it's a symmetrical beam height and width based on a misunderstanding of the Luftwaffe source documents. But this is where it gets confusing, because at the same time that they claim that the beam height and width would be 0.3 degrees, which we'll come back to that number in a second. But they also assume that there's no vertical height limit to the signal, which is kind of counterintuitive to each other. So either it's 0.3 degrees width for both the horizontal and vertical axes, or they claim there is no vertical limit while making a contradictory statement that when asked what the vertical divergence or beam width is from the antenna, they say it's 0.3 degrees. It's difficult to get your head around. I'm not surprised if there's anybody here who's just as confused as I was when I first heard this. Now, Derby being the target, they also base their radio calculations on this. So based on the RF measurements that we just went over, the signal has a 0.066 degree beam width, less than 1 degree, basically half of 1 degree, or half of what, a lot narrower than what it is. So, we're talking about, half of 1/10 of a degree. So the center of the beam, according to their diagrams, would be from Derby, who is 5, which is the distance is significant. According to their calculations, the beam would only be 567 meters wide. Dad stuff. So the center of the beam would be basically just short of 19,000 meters high, or a total of over 12,000 meters above the bomber's max ceiling. According to them, for them to have refraction, it would require a refraction value of basically 0.8 or 5 times the radius of the Earth. Now, when they make this claim, they say it would then therefore the signal would have to be 7 miles high and would be completely unusable as a navigational beacon because it would be too wide. Now, notice what I said. If the beam was 7 miles high, it wouldn't be used as a navigation beacon because it would be too wide. That implies the symmetrical nature, or their understanding of it, the signal being a symmetrical nature, like a cone shape or a rectangle or something like that. But there's fundamental questions that we're going to have with these because, again, these are claims. Like, what evidence is there that the VHF frequencies do not refract? Are they truly optical line of sight? Surely there must be something that they can quote. Although we know that radio operators can account for a radio horizon by using 4/3 R. What's the point of us having that calculation then? Why does the real world need a benefit of doubt measurements when actual measurements are available? What scientific evidence is there that Earth's curvature clips the radio signal? Bull Knight, stop laughing. Is there a propagation method that might actually increase the range of the Knickerbein system beyond optical line of sight? And furthermore, are radio signals symmetrical? Is there a method to calculate the vertical beam width based on measurements? Spoiler alert, the answer is yes. And regarding Derby, the RF measurements have so many complications as we just talked about in the last chapter. But why does the Luftwaffe bomber need to be in the center of the beam? Oh, that's right, because it clips the radio waves at the optical horizon. Is anyone else seeing how this is circular in fashion yet?
Quick question.
So let's talk about the radio horizon. Yep.
I don't know if you're going to bring this up in the future, but Doofus had asked if it had been mentioned that the 400 to 500 yard width is the equisignal and not the beam lobes. I don't know what that means.
It was the equisignal. Yes. So over Spalding, so the Knickerbein system, the dots and dashes, so the side lobes, right? They had a 12-degree horizontal width of beam divergence, but they were able to overlap them to a 0.3 degrees to be able to go out there. So when they found it, they measured the equisignal at 400 to 500 yards. So that should answer Doofus's her question.
Okay, got it. Thank you.
So let's talk about the Knickerbein radio horizon. Now, interesting enough, the same person that they quote in their presentation, Eckersley, is renowned for his research into not only radio refraction, but diffraction as well. So this is a well-studied phenomenon that is backed by empirical evidence. It's something that was novel in 1932 and not novel now. It's basically everyday common occurrence. What it does is basically that the signal can basically refract over the curvature to about 30% further than an optical line of sight. That's what we call a radio horizon. Now, there's multiple calculators online that you can put in your height, and you can find out what your radio horizon is, just like you can for an optical horizon. However, you have to know to look for a radio horizon, which obviously the ether cosplayers do not know how to do. They may not even know it exists. Tend to think it's the latter one. So radio signals are not limited to an optical line of sight properties. The RF waves typically refract downward due to atmospheric variations in the vertical gradient, as we call it. The radio horizon is calculated using an antenna height, and then we multiply it by 4/3 of the Earth's radius. Radio waves are not clipped by curvature. They will actually diffract around obstacles, including curvature, depending on wavelength. Now, one thing that came up during MC Toon's debate was this constant thing like, if it diffracts, and that means there's too much air involved. Here's the problem. When you deal with diffraction, the angle of incidence matters more than anything else. However, when you're dealing with curvature, your angle of incidence is always going to be basically 90 degrees or 180 degrees. Basically, it's going to be complete, or 90 degrees. It's going to be perpendicular because the signal is going outwards and your curvature is basically all around you. This isn't like a building that's only getting part of it and it's going to diffract different ways. Now, the other thing about diffraction also comes down to is that when we get diffraction, we get these side rays that kind of go off and everything else. The amount of power in the signal, and that includes things like the transmitting power, the antenna gain, and everything else. So your radiated power is what's going to define how strong those signals are. So there's entire pages of math equations of how to configure things like refraction and diffraction and things like that. And it takes into consideration things like your radiating power and all these other things like atmospheric conditions and things like that. So, but let's just say that, let's simplify this across the board. Let's say that as we hit the curvature of the Earth, a signal that is from a very powerful transmitter with a very large antenna is going to hit the diffraction at exactly 90 degrees perpendicular. And now all of a sudden, that signal gets spared out by, let's say, a quarter. So let's say a quarter continues on, 3/4 ends up diffracting lower. And it hits curvature again, diffracts a little bit more, diffracts a little bit more, diffracts a little bit more. So let's say that in that sense, it goes, it slowly becomes more, weaker and weaker and weaker. One of the issues that you have to deal with when you're dealing with building what we call a link budget between a transmitting station and a receiving station is the transmitter and its power, the antenna design, things like polarization, things like that, as well as the receiver sensitivity and things like that. So all these different variables, we're talking about like anywhere from 5 to 10 variables, are calculated and put together to decide whether or not the link budget would even work before you even go in the field and start putting things up, because you have to know whether or not it's going to work in adverse conditions besides just, obviously optimal conditions. And all this is done before they even leave the lab, before someone even leaves their notepad to go build something. So one thing we did have access to is the Luftwaffe documentation, and it's basically, it states that it provides us with measurements. And actually at the bottom of it, it says that the optimal range is varied based on humidity and temperature of the air layers between the transmitter and the receiver, which means it will likely be shorter in winter than it is in summer. Why does that matter? So let's talk about Cleve for a moment. The top picture here is basically a panoramic view of that Bull Knight was happy enough to show me of looking from Cleve towards the UK. Now, if you notice the red line, I think it's red, I'm colorblind, forgive me, just to the right of the west, is we have that's basically the view from Cleve towards Derby. That's putting in GPS coordinates of the locations and everything else. So this panoramic view, if you notice, there's no peaks, and that the relatively flat topology near this red line, which is the view towards the Derby. Now, specifically, Cleve and Stolberg were used primarily because of their topology. They had no natural obstructions. Stolberg was basically just across the North Sea, right at the UK. There was nothing in the way, and actually, the salt water actually would help the signal by providing a good conductor for it to continue on. The same thing applies to the lowlands of the Netherlands, which is flooded and wet, as well as across the English Channel. So
Norfolk's pretty flat and wet as well.
yes, exactly. I was going to get to that next. It's like it's not like we're hitting the cliffs of Dover with the signal. Now, since we just got done discussing the radio horizon, maybe it's time actually we do some math with actual measurements. Remember, the Ether cosplayers used an elevation of 200 meters with a LOS horizon of 51 kilometers. However, if you go to the site of the actual Cleve transmitting antenna, the elevation is only 84 meters, and its line of sight horizon for optical is 35 kilometers. Now, their radio horizon is 41 kilometers. Now, there's some source documents where they did some measurements of the signal as it left the antenna, and it's at ground level up to almost 55 kilometers. And then at just short of 100 meters in altitude, at basically an altitude of 100 kilometers. Here's your two basically ideas of diffraction and refraction being exposed in a simple graph. So why is this significant, basically? Because we can see the radio signal characteristics looking at this graph. So I'm going to zoom into a specific one down here in the bottom left-hand corner, and I'm going to bring up the measurements from the previous slide that we talk about the individual altitude of Cleve. So the transmitting antenna is here, this little dot here in the corner. Basically XY axis, right? Not difficult. Each one of these lines is 20 kilometers. And what we have is, actually, let me go back one. I want to make sure I had that. Okay, yeah, so this first line is 500 kilometers. So this is 500 kilometers here high. So from Cleve, we got basically going out to roughly about 50 kilometers, we can start seeing a divergence from here. And then we can see it slowly go across this. So If the optical horizon clips the signal, right, this means that at 35 kilometers, which would be roughly right about here, there should be a diagonal line going straight up. It should be going from this point here, going straight here. There should be no more further going along. There should be no gentle curve as it diffracts around the curvature. There should be nothing else but a direct diagonal line from 35 kilometers outwards, which we don't see. So this lower audibility limit line here, as I call it, should basically stop here and diagonal out. There should be no flatness that goes through this or whatsoever. But the graph counters this by specifically showing how it continues outwards at a low level, showing not only that it refracts, but also that it diffracts around the curvature. So here's your proof in the pudding, so to speak, without having to go anywhere but look at the actual source documentation of the people who designed the system, not an observation from an aircraft 6,000 meters up using a civilian AC-powered ad hoc design in an aircraft on a cloudy night trying to listen in on a static. So one of the most important variables when it comes to the radiation pattern of an antenna is polarization. So there's not much use for a horizontal polarized circuit, except that it could provide a large coverage. And if you're going to bounce it off the ionosphere, you can continue with that large coverage. For something like radar or something like a navigation beacon, vertical is the only way to go. And what this is if a radio signal has a electrical field and a magnetic field, they're basically, let's consider them like an XY axis, right? Polarization pertains to the electrical field. So if you were to look at, let's say, a piece of paper and you're to hold it flat in front of you, and you're going to look at it from on edge. So if you look at it on edge, you see it's very narrow top to bottom. But if you look at it from the top, you see it's very wide from left to right. That would be the representation of like a horizontally polarized signal. Alternately, if you turn the paper vertically, so it's now up and down, and you look from the top, you see it's very narrow left to right. But if you look from the side, you see top to bottom, it's very wide. That would be a representation of a vertically polarized signal. Now, the Nicobine system is a highly directional, vertically polarized beacon with a very powerful transmitter. And we can see this in the pictures of the radiation pattern that was put through. If you notice in both of these, and I'll come back to the difference here in a moment, that if we look from the top down, it's very narrow left to right. But when we look on the oblique views, we can see it's very tall. This basically implies that it is a vertically polarized signal. And this is what you'd want from a bomber. This way, they don't necessarily have to be at a specific altitude to to receive the signal. And you can keep it very narrow, which is what the basis of the Nicobine system is, to be a navigation beacon, to be narrow. Now, these two pictures that are on this slide that I just pointed out here, they're based on the 4NEC2 antenna modeling software. Now, I got these from Frank Heller's website. He did a amazing amount of background and was actually one of my primary sources for this presentation regarding Nicobine. He is a huge fanboy of the S27 receiver, and he was doing it basically to outline the benefits of the S27, as well as the difficulties that the RAF had, and basically just being a radio nerd, it was right up his alley. He just wanted to delve into it. He delved into these things to a level I have hardly seen on most topics. So he was able to put in the antenna specifics and the transmitter specifics and basically get a not the transmitter, but the antenna specifics, and get a radiated pattern of what the antenna does, what the signal would look like coming out if we could see it. But what I want you to notice is, you notice that these are two very different pictures, especially when we look at the obliques. The ether cosplayers typically use this top picture. This top picture is what we call the free space model. This is basically the theoretical model, no obstructions, no outside influences. This would be indicative if you were basically pointing an antenna straight up. Basically, you're going into the atmosphere, going out into space. That's what the free space loss or radiation pattern would look like. The bottom picture is a more realistic picture for an antenna of a 10-meter wavelength from an antenna that is close to the ground, like Nicobine was. You'll notice at the bottom the influence of ground wave propagation. When we talked about conductivity and the dielectric constant of the Earth, why these sites were picked specifically in Stolberg and Cleve was because of the conductivity that was in front of them. We can see that it influences this radiation pattern, that the lower lobe far exceeds the upper lobe. So based on the calculations of all the variables, from the frequency, the characteristics of the transmitter, the receiver, the antennas, the heights of the transmitter and receiver, the terrain and ground conductivity of the Netherlands, the English Channel, and the North Sea, and the total ground range ground wave range, would be extended from about 400 to 450 kilometers from the transmitting station. Probably something they should have looked into first. This right here, these patterns in a different view, this is what Bull Knight tried to explain to the Ether cosplayers to keep them from embarrassing themselves. He specifically said everything I just said, but used smaller words and was dismissed. I should have thought twice about that. Now, I didn't go into all the math and everything else because I didn't want to bore everybody, but here's some of the math equations we used when we talk about radar horizon. You can also, include heights of the transmitter and receiver, or just the transmitter itself if you're going to an area and you're just trying to find one from one location. So this is from the transmitter to anywhere. This is from a specific transmitter to a specific receiver where you take in consideration heights. When we try to convert between beam radians, which is what we use instead of degrees, but then we can also use degrees as well. So you can convert into beam radians to kind of figure out your tangent or your tangent equations to find out the beam width at various distances and things like that, which is basically radians times the distance in meters and things. So now let's go back to the actual claims. I'm not going to read everything on the left. We already read that. Who cares, right? That hasn't changed. Well, it may have. It's been 15 minutes, so it's flare, so it may have changed, but let's assume it did. So we just found out that VHF and UHF frequencies are subject to refraction. They have a calculated radar horizon extending the line of sight 30% further. We used actual elevation measurements and the horizon measurements, and we can see that the signal extends beyond the radio horizon. We see that we saw from the measurements as well that the ground does not clip the radio signal as they say it does. The signal propagates with refraction and diffraction as well as ground reflection. And the signal is measured near ground level at almost 100 kilometers. Radio signals are not symmetrical in practice. This assumption, basically discounts all their variables such as antenna design, polarization, and basically like how the antenna is designed. In this case, the Kinikabine had literally two arrays stacked one in front of the other. This allowed it to basically be highly directional. They used the second, but the array behind it was actually used as almost as a reflector to basically ensure all the power went towards the front of the antenna, not necessarily the sides, or behind. And from our measurements of where the radio horizon was and the height of the actual and the height of the signal as measured by the Luftwaffe, we can see that the vertical beam width was calculated around 5.25 degrees. Oh, look, I was able to do the math to find that out. It's not infinite. And based on these same calculations, we're looking at basically an equisignal beam width and derby would be roughly 2,800 meters or almost 3 kilometers wide, but it would be 48 kilometers. So now we're done with the technical part. I appreciate everyone who's still here and hasn't fallen asleep yet. Has anyone got any questions regarding the signal part before we go into some more fun things?
Yes, I have a question.
Sure, Doc.
Yeah, I will admit I came in a little late, so I may have missed it. But, I was told by Alan that the Jews had something to do with it. Did I miss that part when you went over?
No, I'm sorry. That comes later, so quit being a spoiler. We're going to get to the Jews later.
Okay.
So let's talk about the accuracy. Now, Bull Knight has spent more time in the Ether cosmology. I think he's the only one who hasn't been banned from the Ether cosplayer server. I know I haven't been in there yet, but I've heard multiple times, and Bull Knight has validated this for me multiple times since he subjects himself to that derpiness more times than I can count, that Kinikabine was accurate. It resulted in untold damage and thousands of deaths. After all, why didn't it? I mean, we're talking about it's only 0.066 beams wide. Any aircrew could drop a bomb on that kind of if we can follow that beam and drop and hit a target. You're right, Doofus. If I don't go, I can't get banned. I'll probably get banned after this. So let's talk about some locations here. Let's just do some quick math, like an endless furry convention. Okay, in that case, I won't be going anytime soon. All right, so the Rolls-Royce Limited factory in Derby. Okay, the actual building is actually called Marble Hall, and it's still standing to this day. It is located at these GPS coordinates. It is at this elevation. I'm not going to read all these things. It's here. And then what we do is we also have the cleave measurements and things like this. And then we have the measurements based on true math and not the cosplayer math. Now, true math means that the The Cleve signal would be almost 3,000 meters wide, and the Stolberg one would be almost 4,000 meters wide, or basically we're looking at 10,000 square kilometers wide target area. Now, that's assuming a perpendicular meeting point between the two beams, but however, they hit it oblique. So since they hit it oblique, it's actually larger than 10,000. It's going to be at a weird angle. Not exactly accurate, but I want to talk about Derby for 1 second, well, maybe a little longer than 1 second. So the Rolls-Royce factory was hardly the only target in Derby. Another target would have been the train station, because the train station was actually not only responsible for building almost all of the steam and diesel engines within the UK, but also was repurposed during the war to build the Matilda II and the Churchill tanks. It also did aircraft components. It also did other things. I forgot some of the other ones that it did, but we're talking about like all the locomotives to move the material around the UK during wartime efforts, all the materials that were being made there. The entire area of the Derby rail yards basically equated to almost a couple of 100 acres. Not exactly a small target, but as we look at the math, we're talking about 10,000 square kilometers of a target area. But if we use the RAF observations, the target area would be 800 meters by 600 meters, or basically less than 1 square kilometer. If it was 1 kilometer wide, which would be easy for a squadron of highly trained Luftwaffe bombers utilizing equipment specific for Knickerbein, flying in formation to hit a target within that 1 kilometer. I mean, hell, I think even we could do that. But how many times did the Luftwaffe actually bomb Derby? And how much damage was caused by these bombings? You know, if only some research entity somewhere had consolidated all the bombing reports in the UK and the number of casualties during the Battle of Britain. I don't know, maybe the UK National Archives located in Kew, I think it is.
Yeah.
At the top here is a snapshot. It's in Kew, right, Alan?
Correct.
Okay. Lucky for us, they have a spreadsheet of this. If you ask them nicely, they send it to you. This spreadsheet catalogs 32,869 bombing raids in the UK from September 6th, 1939 to July 2nd, 1942. Now, if you notice at the spreadsheet on top, we only have one filter applied to this entire thing, and that is the Civil Defense Region, actually two. Civil Defense Region, which is North Midlands, which is where Derby is located. And the only reason why that was done is because the amount of cities that they locate are huge. So I wanted to kind of limit my scrolling. And I basically filtered on all the reports for Derby. Now, this resulted in a total of 7 bombing raids, of which 6 were at night. The 7th one that was here was actually done by Junker, and it was the only one to actually cause damage to the Rolls-Royce factory. Now, I want to pause here on just the spreadsheet for a moment. We just got done talking about the Derby rail station and what a major contributor was to the war effort. We're talking about, marshalling yards, sidings, the locomotive and coach works, which are actually building tanks. We're talking about other transport vehicles. We're talking about aircraft components. I mean, you have 2 high-value targets in Derby. Why didn't the Luftwaffe target Derby more? Why is it only 7 times? Why is it only 6 times at night where it's typically safer? Why was there no reported damage to the Rolls-Royce factory or the Derby rail yards manufacturing facilities prior to 1942? I mean, London was bombed a total of 5,653 times. Bristol, which is located only 125 miles away from Derby, it was home to the Bristol Aeroplane Company, which built the Blenheim bomber. It was bombed 39 times. Portsmouth, which is home to the Naval Dockyard and was vital for shipbuilding and naval repairs. That was bombed 56 times. But Derby, home to the production of tanks and military transport vehicles, and the sole manufacturing plant in the Merlin V12 engine, which was responsible for the air defense supremacy of the UK, was bombed a total of 6 times. Why didn't they bomb it more? Because the Knickerbein's accuracy is better represented by the Luftwaffe documents than the RAF observations. Derby was just too far for Knickerbein to be accurate enough for extensive use. So let's go over some of the source documents that we have. Some of these I'm going to kind of breeze through a little bit. I'll make this available for people. Here's some of the general specifications. These are translated from a Luftwaffe memo. This goes into just the system requirements, where we're talking about, has to be based on the Lorenz system, the beam width, dots and dashes, things of this nature. I had to be used for the FUBL1 receiver, things like that. They also had a list of very laundry listings of site requirements. So before a site could be considered a candidate, it had to meet specific requirements, things like unobstructed views, no terrain bumps. The terrain at the beacon site had to be flat. Unobstructed view to a defined reception point at 1 kilometer away from the antenna, and preferably to the horizon beyond it. Wait a minute. Horizon. That implies curvature, doesn't it? Here's the specifics to the Knickerbein antenna. Now, this thing is huge. It is 93 meters wide It is 30 meters high. It is 300 feet wide and 100 feet high. Now, if we look here, this is the center strut here. Each side of this is basically one side. So this would be the dots. This would be the dashes. And then where they overlap, they use they create a V angle. So if you see here or the top here, this is the V angle here. They create a V angle by moving these two, either pinching them together or spreading them apart to be able to get that overlap of 0.3 degrees. Each subbeam, so each half is basically, like I said, it was a linearly stacked array, consisted of 2 rows of 8 vertical dipoles. And then there's also the exact same array behind it that was kind of used as a reflector to get the signal to go forward, not backwards. It could not be adjusted for elevation. And each signal or each specific frequency or each specific transmitting site had its own frequency. Something else we had access to was going to be some documentation regarding navigation. So, and this is also the operation of the system. Now, these are like basically translations, the top of the top picture, the bottom of the bottom picture. Just want to point out a couple things. Notice the translation specifically noted that the range increases with altitude. Why would that be on a flat Earth? The bottom document stated that the flight altitude given contained average values. Now, these would be the average measurements across various antenna types and radio receivers. This is important. We'll come back to this in a moment. Now, we talked about this graph a little while ago. We're talking about the signal propagation and radio horizons. Well, now let's look at the graph as a whole. This is the classified document. This was part of the aircrew training. Since it was classified, it could not be taken into the aircraft. Of course, radio operators being radio operators, they took notes. It happens. Now, when we talk about average values, we have the lower audible limit here. We have the upper audible limit here. Now, when we were at 60 kilometers, we were basically right near zero. When you take the height of this at 5,500, you take the bottom of it at 0, and you do the math, that's where you get the 5.25 degree beam width on a vertical axis. Now, when we talked about, and when we're talking about average values, the Anson intercept flight intercepted the signal at approximately 5,600 meters. And the distance between Spalding and Cleve is roughly 440 kilometers. That puts the intercept flight at right about here on the graph. Now, considering all the challenges we talked about regarding the measurements versus observations, it is practically incredible that they located the beam at all. I mean, this is an analog signal. They don't necessarily, this is an average signal. So it could be lower, it could be higher. It depends on the receiver and everything else. But we know that the receiver that he used was not built for this. It wasn't as sensitive. It was flying at 6,000 meters up, and when it was built to be inside of a house, it's negative 10 degrees. Now, electronics usually work better in the cold, but still. But this is an analog signal. So like your radio station, you start getting static. So in a sea of static, they were able to locate a 400 to 500 yard beam width here. Now, do you think maybe if they heard it here, they may have got maybe a different, they would have got more accurate measurement of what it actually is? I mean, if we look at here, again, this is the source documents from the Luftwaffe. From the transmitting station here, this is 1 kilometer, this is 2 kilometers. If we go out 440 kilometers, which is where Spalding was, right? This beam width is going to be roughly plus and minus 1.5 kilometers. It's going to be 3 kilometers wide. Hey, isn't that what our math just showed? Amazing. Now, actually, hold on. Amazing is the wrong word. Let's quote a flat earther. Let's say interesting. So let's talk about measurements. Now, if you're still with me at this point, thank you. I promise we're on the last technical slide before we start just doing some shit talking and things like that. But like the graph before it, this is one of the most important slides. This is a table compiled by, if you notice here, it says the chief NVM, and it also says that it is the NVM here. Oh, sorry. So it's from the chief NVM and LC4 from June 1st, 1939. Now, NVM stands for, I understand German, can't speak it very well, so I'm not going to try to butcher this, but basically it translates into the signal testing service. So it's Nachrichten Versuchswesen, and LC4 stands for Luftwaffenkommandant, Section 4. Lung 4, I think is what it is. But either way, it's the Section 4. This outlines the specific testing variables and measurements made by the Luftwaffe in these 2 specific units. Now, to provide a little context of the transmitters tested, I basically took this, translated. I had a German native speaker help me out, and for those who don't know, he's Danish tech guy on Twitter, and he helped me basically put this together. So what we're going to do is we're going to look at this very quickly. Everyone knows how to read a spreadsheet table, I hope, but I'm going to go through this quick. So we have the different devices that we have. We have a total of 3 devices. We have the LFF, which is the Lorenz basic system. It transmits at 500 watts. We have the FF and FD low. This basically equates to the small Knickerbein, which is the version 2.0 that was more mobile. That also transmits at 500 watts. We have the FF and FD. This is the large kinetic combine. This is the 3,000 watts transmitter. You can notice the beam width here being 1.5 degrees down to 0.2 and down to 0.1 degrees. They never reach 0.1 degrees on the large kinetic combine, so they're out of luck. By the way, Shane put both of these values into AI to find out what the decimal value was, but I digress. The next block we have is energy bundling. If you guys want to know about that, we can come back to that. It's sort of important, but not really important to what this slide is actually going to go into. It's a little more technical. So across the top here, we have 3 different receivers. We have the FUBL1, which is without a change. We have the FUBL1 with a coupled feedback, which is basically a slight modification that isolated feedback and allowed to make it a little more sensitive and cut out some of the ambient static and stuff like that was inherent on the first one. Then we have one that translates as special device. You gotta love intelligence weenies. They don't give you any sort of information of what that is. Now below each one, we have 2 different antennas that were done. We have what's called a stick antenna or a whip antenna. It's called MIT stab, which means with pole, but it means a whip antenna or a stick antenna. Those are the little sticks that are on the fuselage or on the back of your cars for your antennas, for your radios. Hanging antenna, which is basically it's a wire antenna that's hung off that is reeled out from behind the airplane that allows them to receive. Again, there's a stick and hanging antenna for the coupled feedback. And then for the special device, we have a transverse antenna as well as a hanging antenna. The transverse antenna, picture basically a wire that goes from wingtip to wingtip and elevated above the fuselage as it crosses. It's basically just basically turns the whole wingspan into an antenna. Now, the note down here at the bottom, it says the range is likely to be dependent on humidity and temperature of the air layers between the transmitter and receiver, and the range decreases as humidity increases. We talked about this before, shorter in winter and in summer. So these are the actual distances that they measured. So when we're talking about like a stick antenna with an LFF device, they got a range of oh, by the way, this is at 4,000 meters altitude. So at the stick antenna, they're able to measure it out to 270 kilometers. With a hanging antenna, 370. Again, same values here. And then when we get to the large antenna, it goes up to 400 from 270, goes up to 500 kilometers from the hanging antenna. I'm not going to go through all these, but you can basically see that so the special device, while it's not necessarily annotated, one of the things it could have been the FUBL2 is the civilian version of the BL1, but the FUBL3, which came out in 1941, I believe it was, that is more of the military version of the FUBL1, so that probably is the one that they were talking about as far as special device. It basically had a lot more shielding, a lot more advancements in circuitry and amplification and things like that. So as with most things, when we're dealing with a bullshit fallacy and the amount of time that we invest in something that someone spent 30 seconds to say nah onto, I end up down a rabbit hole. I got curious. How did they measure this? Now, they don't actually note who actually measures, but one thing that I find interesting is that while I was doing my research, I found out that there was the LZ-130, which was the sister to the Hindenburg. It was called the Graf Zeppelin II. Now, since the Hindenburg sort of, caught fire and killed a bunch of people, they were not going to allow any more hydrogen-based Zeppelins. So Germany had worked out a deal with the U.S. to buy helium from them, which is inert, and they were going to use it for the same purposes. The Grand Ambassador of the Third Reich, visiting everyone, coming to a tourist trap near you. Now, a certain mustachioed man decided to get a little big for his britches and started to be aggravating some of its neighbors. And by 1939, the U.S. said, no, we're not going to sell you any helium. You're out of luck. So they had to use hydrogen. Now, because they're using hydrogen, they could not use people, but they had spent all the money and built this thing, so they had to find some use for it. Now, the interesting thing was the Signal Corps, and this is back to that guy Martini and some of those others from the cast and crew. They decided to use the LZ-130 for electronic intelligence prior to any large-scale engagements. Basically, it did multiple missions where it carried instead of people, it carried receivers, and instead of lights in the sky and propaganda, it carried antennas to intercept. Basically, it was used to intercept and map the frequencies and capabilities of their potential adversaries. One of its missions was it flew basically through the English Channel along the coast of England, still in international airspace, then hung a nice left and went north past Norwich and everything else, all the way up to Scotland. And during that time, what it did, it didn't feigned engine trouble, started floating over the land, and then they finally fixed the engine and was able to return home. Now, what they were able to do is they were able to not only see visually, but also listen to the electronics signals and radio signals to learn what the British capabilities were. And that was twofold, to learn if A, they had radar, and B, whether or not the frequencies that were being used for Kanikabine would be interfered with by something else. Now, they weren't able to locate radar because they assumed that the radar was going to be similar to their radar in the higher frequency ranges, not the lower frequency ranges. So while they saw the towers of Chain Home, they had no idea what they were. They still put them on a list of things that, to target by the bombers, but they really didn't understand what they were at the beginning. They found out, obviously, much, a little bit later.
They actually assumed it was a radio navigation.
Mm-hmm. And it was they weren't really looking at that level. When they did look at that level, they were looking for pulse signals, and they heard some pulse signals, but they actually, and it was Chain Home that they listened to, but they thought it was actually a German signal because there was no direction finding. They thought it was a German signal that was coming from Germany and other places, and therefore it wasn't actual radar because a radar wouldn't operate at that low level. So when I said that they were developed independently of each other, but very different, that's your biggest clue right there. But I just thought that was an interesting rabbit hole that I went into. Now, the HE-111 could have still been the one that they used on record. However, I think it's a decent possibility and even maybe a probability that the LZ-130 was used for these measurements because, it's the ideal platform. It can hold its altitude. It goes slow. It was already there listening for everything else anyway. Hey, why don't you listen for us also? Makes sense. It's around the same time frame. It's not far out of the realm of possibilities.
If this is recordings or measurements made before the war started,
yes, 1939.
they wouldn't be using HE-111s off the English.
Oh yeah, you're right, because that would be a military aircraft. So why would they do that unless they're using a civilian?
Because they would. Because they would. I mean, yes, there were some. The Lufthansa did use them as a commercial air, but the problem you've got is you'd have to get it there, flying it out of northern Germany on. And remember, it's a medium bomber. It hasn't got the range necessary for that type of reconnaissance.
To me, when I found this out and I found that they were using the Zeppelin for ELINT operations, one, I come from a signals intelligence background. It automatically piqued my interest. It was a welcome rabbit hole to go down. But as I read more and more, I'm like, this has to be the way they measured it. I mean, it just makes sense.
Yeah, and we would say outside of because back then that was 12 miles off the coast.
Mm-hmm. Oh yeah, they went right up the side of the coast, and they feigned engine trouble, and they started drifting over land. I don't know if they got up as far away as Scotland, but they got up pretty far north, and they called in saying they were having engine trouble, and their controllers were keeping an eye on them, and mysteriously the engine came back in after they drifted over land for a little bit, and then basically to give them more of a view inland than they could possibly receive. And then they turned around. I mean, one of the things that the Zeppelin had is they had what they call like this little capsule that they could drop out of the bottom. It looked, they used it for, in World War I for visual search. They would basically drop this, it's almost like a little metal Zeppelin, and they would put somebody in it and they would drop it down. And the Zeppelin would hang up above the clouds, and they would drop this down below the clouds so that somebody could, obviously visually look at things. Well, they did the same thing, just put antennas on it because of the structure of the LZ-130 with the metal frames and everything else. They found that the antennas weren't very suitable being on the dirigible itself, so they actually had this capsule they dropped below it to be able to listen in on some of the signals and things. Sea of Kanikabine. It was the grandfather to various navigation systems we use today, like the ILS and the VOR. It was the first instance of electronic warfare and led to the development of technologies and strategies that we still use today to not only protect our own communications and signals from being jammed and intercepted, but also how to counter adversaries doing the jamming and intercepting of our signals. These are used today in the military 80 years later, and it reaches even further into the future with the development of radar and GPS guided ordnances. So lastly, let's talk about the reality of the Battle of the Beans. Kanikabine was an ingenious adaptation of an existing system. It was the opening salvo of a secret war that, while it only played a small role, it was a significant role. It proved the value of science over skepticism. It proved that science, technology, innovation, and intelligence combined were just as crucial as actual weapons comparable to the Spitfire, the Churchill tank, and the Vickers machine gun. Consider the innovation part of this. Radar went from a large ground-based antenna and transmitters to an aerial platform capable of leading interceptors to bombers without a ground relay within 4 years. Largely, the Battle of the Beams is an unknown battle. It's known to specific groups with interest in the fields of radar, or radio, or signals intelligence, and often not the entire, usually specific parts. It's a topic covered as a case study during my technical training when we talked about signals intelligence and how signals intelligence is used and exploited. And maybe, hear me out, maybe we should thank Flat Earth for bringing this subject back into the limelight. Maybe we should thank them for bringing something so nuanced and largely forgot into the limelight. You know what? On second thought, no, it's not. But let's review the claims by the Ether cosplayers of how Kanikabine proved the flat Earth. No, since we started with a quote, sorry, I got a little click happy here. Since we started with a quote, let's end with a quote. And I find this just as fitting as the beginning quote. Julius Caesar said, of course, in Latin, experience is a teacher of all things. It's really one thing to learn about a theory. It's something else entirely to apply it in a practical sense. So hopefully, I have shown how fundamentally flawed the assumptions and calculations are that are the linchpin of the cosplayers' claims. They looked at only one part of an overall system, the signal, misunderstood it, and ignored everything else. Threw the baby out with the bathwater, because this is what my confirmation bias says. By everything else, I mean that not just the difference of the equipment between the RAF and the Luftwaffe, from the airframes to the receivers, they ignored the sight system requirements, the antenna designs, the radio propagation. When I mean everything else, I literally mean everything else. Now, were they duplicitous in their measurements, stating that they were giving the benefit of the doubt measurements of the globe model? Or did they not understand how to calculate what the radio horizon was? So therefore, because they saw the divergence at around 50 kilometers, they worked backwards to say, what's the optical line of sight? Because they didn't understand what a radio horizon is. Or did they intentionally hide it? Were they needed to hide the characterization of the signal about how it refracts and diffracts around the curvature? They glossed over research by Eckersley, regarding radio wave refraction. In fact, his paperwork on ultra shortwave refraction and diffraction was written in 1932, I believe. But yet they considered that hand waved away, and they sit there and say, oh, that's just discussing omnidirectional broadcast. Interesting thing. Omnidirectional broadcasts still are subject to things like refraction and diffraction, so why wouldn't it apply? Lastly, and most importantly, they banked heavily. Like they went all in on a bet of Texas Hold'em on the RAF signal observations instead of the Luftwaffe technical documents and measurements. We should be asking why. Why are these things omitted? Why were they dismissed? Well, I can only come up with two reasons. They either didn't understand or they did it on purpose. So without presupposing the globe model of Earth, or what we call reality, the fact is that Kanikabine would work on a globe. It would also work on a dirt pizza, home to the flat Earth, but not in the way that the Ether cosplayers describe it. Remember the picture that we saw in the beginning that just showed a flat line and a triangle and a plane in the middle of it. But it doesn't act that way. After all, there would be no need for a lower audibility level on the signal graph, nor would the RAF had to have sent planes up to locate the beams. They could have been heard at ground level. But why does the lower audibility limit rise with distance? Why are altitude and range variables closely tied together? Because the Earth is a sphere, that's why. Kanikabine accounted for and is evidence of curvature. Globe wins again. Now, thank you for your time tonight. I'd like to thank my fellow radio aficionado Bull Knight and our resident radar specialist, Alan, and others for the collaboration on this project. Their input and assistance was invaluable to this finished product. I sincerely hope you enjoyed this presentation ending as much as I did when I finally finished it. All kidding aside. I mean, seriously, fuck was I happy when they finally finished this. I mean, just like you're happy, it's over. This was a labor of love. And while I complain about it, this took the bullshit fallacy to a new level of investment. And I'd be lying if I didn't say I enjoyed every minute of it. So thank you for listening. Hopefully I helped shed some light on this. Hopefully I had made it less of the silver bullet and more of the silver pacifier for the cosplayers to suck on some. And as we say for Unfornicated, we can't unfuck stupid people, but we can unfuck the stupid things they say on social media. And thank you for everything else. So if you guys have questions, now's the time.